In this segment, I want to talk about how we define functions using recursion over lists. And what I'm going to do is start with an example, the example of adding up the list 3, 2, 4. Let's look at how we can build up the sum of a list, writing a table. So what we're aiming to do is the sum of the list 3, 2, 4. But we can start off by writing a table of sums. The empty list has sum 0, the list with just 4 in it has the sum 4, the list with 2 and 4 in it is 2 plus 4, the list with 3, 2, 4 in it is 3 plus 2 plus 4. Now, as we noticed when we looked at recursion over numbers, you can see that here we can get from one line of the table to the next by adding the number at the front. So here we go. We can get from the line for 2 4 to the line for 3 2 4 by adding 3 at the front. So that suggests that we can say in general something like the sum of the list x cons x's is got from the sum of x's. Here's the sum of x's, here's that same sum, and here's the x. What we do is we add x to the sum of x's. So we're getting from sum of x's to the sum of x colon x's. And there we see a pattern that we can write down as a Haskell definition. And here indeed it is. We're saying here the sum of the empty list is 0, and then the sum of x cons x's, x put on the front of x's, is equal to x plus the sum of x's. Now, we've got that as a definition. Let's see how we can use that in a calculation to get the result that we would expect. Okay, let's use these equations to work out the sum of the list 3, 2, 4. That's a non-empty list, so the second equation will apply, and that tells us this is the 3 plus the sum of the list 2, 4. Now, we're okay writing this because remember, function application binds more tightly than anything else, so this will always bracket like this. We don't have to write those brackets, so in fact I'm going to omit them. And then we can unpack the next. And that says it's a non-empty list, so 2 will match with x, and the list with just 4 in it will match with x's. Let's just say that again. This will match with x. This remainder of the list will match with x's, and that will give us the result 3 plus 2 plus sum of the list with just 4 in it. Now again, we get 3 plus 2 plus, this will match with, here we used pattern matching again, this will match with x, and the empty list matches with x's. So we get here 4 plus the sum of the empty list, and this gives us, by the first equation, 3 plus 2 plus 4 plus 0, which gives us the sum of the list, which is 9. So you can see from this what we can do is use those equations to do a calculation just as we have done before. And when we apply an equation with the x cons x's pattern, we match x against the first element in the list, and x's against the remainder. And we can see we've used that a number of times here, and because that equation applies for every possible list of every possible non-empty list. And just to remind you, I've been using this terminology, x, cons, x's. We use a singular variable, x, before the colon because it's just one element. It's to remind you that before the colon we have one element, after the colon we have a list. So when we do the match, we get a single element like 3 before the colon and a list like 2, 4 after the colon. And we call colon cons traditionally because it's short for constructor of a list. Now, if we look at the way that we defined functions over integers, we had a template that we modelled on what we saw was a general pattern for definitions over integers. And what I want to do is a similar thing here. Let's look at the pattern for sum and see what in general we can say about what a recursion looks like. And the first thing we can say is that we have to define a result for the empty list. The second is we have to define a result for the non-empty list, x, cons, x's, and that result will use the value x and the sum of x's, the function as it's already defined on the tail, because we're writing a function that's recursive over lists. So we're using what we already know about the sum on the tail of the list to define the sum for the whole list. And so this is the form of the template for a function defined over lists, that foo of the empty list is something, and foo of x, cons, x's, foo of a list whose head is x and whose tail is x's, we define from x and foo of x's. One way of looking at the second equation is to ask this question. If I was given foo of x's, how could I calculate foo of x colon x's? So if somebody gives you that, how could you get from that to foo of x colon x's? It's just another way, but perhaps it's a way of thinking about it that's a bit more constructive than just saying fill in here. Let's try this template out. Or before that, sorry, a piece of notation, piece of syntax. When we're writing x cons x's in a function application, we need to put the x cons x's in parentheses, because otherwise the function application would bind to the x and it would mean foo of x cons x's rather than foo of the whole thing x cons x's. So it would mean something quite different, and in fact it will be incorrect, because foo should be applied to a list rather than a single element. So we get a type error if we wrote that. So we need to write foo parentheses x cons x's. If in doubt, add parentheses. Let's try that template in one example just to see how it works. Let's think of writing the product of a list of integers. Well, if you have no integers, the product is 1. Why do we choose 1? Because 1 is the identity. 1 times any number is that number. So that's what we use as a starting point. And then how do we go, if somebody gives me the product of all the numbers in the tail of the list, that is product x's, how do I get the product when x is added on the front? The answer is we multiply the two together. And so what we write here is x times product x's. So there we have us using that template. It's a similar model to sum. And just if you want to get some exercise, try writing for yourselves the functions and, which ands together all the booleans in a list, and OR, which disjoins it, gives you the OR of all the elements in the list. It follows exactly that pattern.